Welcome students. We are back with another lesson. In this lesson, we'll derive an expression for fringe width. So deduce an expression for the fringe width in Young's double slit experiment. For deriving the fringe width, first we have to derive the equation for path difference. Then after deriving the equation for path difference, then we will derive the equation for position of bright fringe and then position of dark fringe. After that, we will derive your fringe width. So in our today's class, I will derive the expression for the path difference and I will derive the expression for position and position of bright as well as dark fringe. In our next class, we will derive the expression for the fringe width and then we'll solve some numericals based on your fringe width. Fine. Consider a monochromatic source. By monochromatic, I means this source is producing light of same color. So monochromatic means one color. Mono means one, chroma means color. So this is a monochromatic source. That means producing a light of same color. That means the light produced from here will have the same wavelength. Clear? So as we know, the light travels as a wave. So you have a crest, you have a trough, you have a crest, you have a trough. Now this light is made to pass through your double slit. That means two slit. Your slit S1 and your slit S2. So now if the light comes out of these two slits, the lights will be coherent source of light. Okay. This coherent sources of light. I will explain this term after I've derived the fringe width. Fine. For now, you can consider your slit S1 and your slit S2 acts as a coherent sources of light. Apart from this, your slit S1 and your slit S2 are placed at a distance of small d away from each other. Right? Now, the light produced by your slit S1 and slit S2 will interfere with each other and produce an interference pattern on the screen. And your screen is placed at distance d from your coherent sources of light. Now, consider this point. The point O as the center of the screen. And your slit S1 is somewhere at, let us consider this point as A and this point as B. And as I've already said, your slit S1 and S2 are placed at a distance of small d away from each other. So your point A and B are also placed at distance d away from each other and they are equidistant from the center O. If they are equidistant, then so it means that the distance between this point A and O is half of this total distance d, that is d by 2. Similarly, the distance of O to B is half of this total distance d by 2. Now let us consider any point P on the screen. Fine. And let us see what kind of interference we got on this point P. So consider a light coming from S1 and falling on this point P. Similarly, the light coming from S2 and falling on this point P. Now, look, are the lights traveling the same distance from S1 to P and S2 to P? Is S1P and S2P equal? No. Fine. So a light which is coming from S to P has to travel an extra path. That extra path will denote as path difference, which will be denoted by small p. So the nature of the interference, that means whether it will be a bright or whether it will be dark, depends upon the extra path the light has to travel. Fine. So P is the path difference between S2P and S1P. Fine. Now consider your right angle triangle S2BP. This triangle. Okay, let me just put this triangle somewhere. This is your triangle S2BP. And now consider your triangle S1AP. Fine, let me put this triangle somewhere. Fine. So look in your triangle S2BP. This is a right angle triangle. In this triangle, the hypotenuse S2P, okay, this hypotenuse, the square of this hypotenuse will be equal to the sum of the square of the other two sides. Fine. So your S2P square equals to S2, your S2P square equals to S2B square and your PB square. Fine. Similarly, look at this triangle. Your S1P square, S1P square equals to S1A square, S1A square and PA square, PA square. Fine. Now let us subtract this two hypotenuse. S2P square minus S1P square equals to S2B square plus PB square minus S1A square plus PA square. Fine. Now look here. This S2B, how much is S2B? S2B is this distance, your capital D. Fine. Similarly, S1A. S1A is how much? This distance is also capital D. Fine. Now look here. PB square. Okay. This distance P to B. How much is this distance? P to O is how much? X. And O to B is how much? D by 2. So PB is X plus D by 2. Similarly, your PA. Okay, look at this distance. PA. How much is this distance? You know, we have to calculate this distance. PA. Okay, this much distance. Now here, PO is how much? It is X. Now from here, if we subtract D by 2, this distance, okay, AO, then how much we'll get? We will get PA. Therefore, PA equals to PO minus AO. So this is X minus D by 2. Fine. Fine. Now let me expand this term. Okay. Fine. Using a plus b whole square expansion, which is a square plus b square plus twice of ab, I can expand this term. So I'll write x square. This will be d square by 4 plus twice of x plus d by 2, which will be how much? Xd. Fine. Now similarly, let us write this part of the bracket. So if I expand this term, d square will be written d square. Now for this part, you can use this identity. A minus b whole square equals to a square plus b square minus twice of ab. So here x square d square by 4 and then minus 2xd. That means 2 times of x times d by 2. This 2 and this 2 gets cancelled, so I have xd. So I will have minus xd here. Fine. Now let us open this bracket and this bracket. Fine. Fine. Now if I open this bracket, this d square x square d square by 4 plus xd remains same. But here if I open the bracket, I have to multiply with negative sign. So this becomes minus d square minus x square, this minus d square by 4, and this one minus xd will become plus xd. Fine. Now here we can cancel the term. This d square and this d square can get cancelled. X square minus x square get cancelled. D square by 4 minus d square by 4 get cancelled. And what we are left with? We are left with xd plus xd. And xd plus xd is how much? This is 2xd. Fine. So let me just rub it and write 2xd here. Fine. So S2p square minus S1p square equals to twice of xt. Now let us expand this term using a square minus b square equals to a minus b times a plus b. Therefore, S2p square minus S1p square can be written as S2p minus S1p and S2p plus S1p. Fine. Fine. So let me just zoom in. Your S2P, it can be written as S2P minus S1P, S, and this one will be plus. Okay, fine. So using this identity, fine. Now what we can do is we can send this term in the denominator. We can send this to the right hand side. Fine. Fine, so I can write down S2p minus S1p as twice of xd divided by S2p plus S1p. Fine, fine. Now we have to consider assumption. Okay, look here very carefully. In practical case, what happens is that your slits, your double slits, is at a very far distance from your screen. Fine. So in such case, what happens? Can you see this distance S1p and your S2p? Okay, when this screen is placed very far from the chromatic or your coherent sources, in such case, what happens? Your this distance S1p is approximately equals to S2p. Can you see? Isn't it? Or I can say both of this distance, your S1p and your S2p, are approximately equals to the distance between the coherent sources and your screen. Can I say can I take this assumption? Yes. Fine, so I can take this assumption. So I can write down in practice the point P lies very close to point O. Therefore, I can write S1p approximately equals to S2p, which is approximately equals to the distance between the coherent sources and the screen. Fine. So if S2p is also equals to D and S1p is also equals to D, then D plus D will give me how much? 2D. So let's substitute the value 2D here. Fine. So twice of XD upon twice of D. Now let's cancel this 2 and 2. So I'll have XD upon capital D. Fine. So S2P minus S1P equals to X d upon d. Now let's go back and check what is this S2P minus S1P. Your is it S2P minus S1P is what? It is part difference P. Fine. So let us substitute this part difference there. So we will substitute your part difference here. Okay. Fine. So your part difference equals to XD upon D. Let me put this in a box. Okay, so this is the equation for your part difference. Fine. Now next let us find the position of the bright fringes. Now consider the light traveling from point S1 to the point P, S2. Consider the light traveling from S1 to P, S2 to P. So the light traveling from S1 to P. Okay, consider one wavelength, two wavelength, three wavelength, four wavelength. So it takes four wavelength for the light to reach from S1 to the point P. Fine. Now let us consider the light traveling from S2 to the point P. Now since S2P is greater than S1P, so light has to travel a larger distance. If the light has to travel the larger distance, that means it will take more wavelength as compared to S1P. Okay, let's take example. You have one wavelength, two wavelength, three wavelength, four wavelength, five wavelength. Fine. So in case of S1P, there are four wavelength. In case of S2P, there are five wavelength. Fine. Why? Because the light has to travel the extra path difference in case of your S2. And that extra path difference is given by this equation. Now, coming back to our topic, look here. The trough and the trough coincides, the crest and the crest coincides, the trough and the trough coincides. That means the lights are of same frequency and having the same phase difference. If the light are having the same frequency or a zero or a constant phase difference, then in that case such interference will be a constructive interference. And if it is a constructive interference, then at this point P, how much what kind of interference you'll see? You will see a bright fringe at this point P. Fine. So at point P you will have a bright fringe. Now let us consider another point on the screen, the point Q. Fine. So now the light is traveling from S1 to Q. Okay. So one wavelength, two wavelength, three wavelength, four wavelength, five wavelength. So it takes five wavelength to reach this point Q. Now the light coming from point S2, one wavelength, two wavelength, three wavelength, four, five, six, and seven. Fine. Now again look, the trough and the trough coincides, the crest and the crest coincides. So again you have a constructive interference. That means again you will have a bright spot at this point Q. Fine. Fine. So at point P you had a bright fringe, and at point P how much was the phase difference? Lambda. Similarly, at point Q you had a uh, bright fringe, and again at this point Q. Okay, this is not phase difference, this is part difference. Okay, correct this one, this is part difference. Coming back to point Q, at point Q also you had a bright fringe, and how much was the part difference? This time it was 2 lambda. Fine. Now let us consider one more point, the last example. Fine, consider a point R. Now the light traveling from point S1, one wavelength, two wavelength, three wavelength, four wavelength, five wavelength, six. So you have six wavelength. Okay. So from point S1 to point R, the light travels six wavelength. Fine. Now consider the light traveling from your point S2 to the point R. So you have one wavelength, two wavelength, three wavelength, four, five, six, 7, 8, and 9. So in this case, the light was traveling 6 wavelength, and in this case, the light is traveling 9 wavelength. Now look here, again the trough and the trough coincides, the crest and the crest coincides. So what kind of interference? Constructive interference. And in this case, how much is the path difference? The path difference is 3 lambda. So at point R also you will obtain a bright fringe. But how much will be the phase difference? Path difference? It will be lambda. So can you identify this pattern? Whenever you have a phase difference of lambda or a multiple of lambda, fine. In that case, what kind of interference you will see on the screen? You will see a bright fringe. Fine, fine. So for now, the position of the bright fringe, okay. So your bright fringe will be obtained when the path difference equals to n times your lambda. It can be your 0, it can be lambda, it can be 2 lambda, it can be 3 lambda, it can be 4 lambda, it can be 5 lambda. That's why I have multiplied this term n. Okay. So if the path difference equals to n lambda, in that case you will obtain a bright fringe on the screen. So from here I can find out the position of the bright fringe. This x shows the distance of the point P from the screen, or distance of the bright fringe from the screen. So if I substitute these values here, d will go here, small d will come to the denominator. Fine. So I can write my position of the bright fringe x equals to n times lambda d divided by small d. Fine. Now again consider your slit and the screen. This point O represents the center of the screen. Fine. Now consider, look here, the light traveling from S1 to O and the light traveling from S2 to O. Fine. So from S1, 1 wavelength, 2 wavelength, 3 wavelength, 4, 5, and 6 wavelength. From point S2, 1 wavelength, 2 wavelength, 3 wavelength, 4 wavelength, 5 wavelength, 6 wavelength. Fine. So complete wavelengths in this case. So you have 6 wavelength here and you have 6 wavelength here. In such case, you will obtain a bright fringe at this point O. Okay. And in this case, how much is the path difference? Path difference is 0. The light coming from S1P and the light coming from S2P, they are traveling the same path difference. Okay, fine. So let's make a table. Okay, now in this case, for the first case, how much is the path difference? The path difference is 0. If path difference is 0, how much is the value of n? N is 0. If n is 0, what is the position of the x? See, this is at the center. Okay, on the distance x is measured from the center. So in this case, x should also be how much? 0. So this is your first bright fringe. Okay, so I, instead of writing first bright fringe, since this bright fringe is at the center, I will write this one as central bright fringe. Fine, now let's consider for this point P. You have 1 wavelength, 2, 3, 4, 5, 5 wavelength. Next, 1, 2, 3, 4, 5, 6. So in this case, how much is the path difference? The path difference is of lambda. If this is lambda, what is the value of n? N equals to 1. If n equals to 1, fine. So now in this case, the value of x, use this expression. Okay, the value of x will be lambda d by d. So at this point you will get the first bright fringe. At point O you had central bright fringe, then at point P you will have the first bright fringe. Fine. Fine. Now let's consider another point Q. So 1 wavelength, 2 wavelength, 3 wavelength, 4 wavelength, 5 wavelength. From point S2, 1 wavelength, 2 wavelength, 3 wavelength, 4 wavelength, 5 wavelength, 6 and 7. So you have 7 wavelength. So in this case, how much is the path difference? It is 2 lambda. If it is 2 lambda, what is the value of n? 2. Then the value of x will be twice of lambda d upon small d. So here also you will get a bright fringe, and this bright fringe will be known as your second. Fine. So if we keep on continue like this, okay. So consider if the path difference is n lambda, where the value of n is n, and this position of this bright fringe will be n lambda d by d. So at that point you will get the nth bright fringe. Fine. So this is the expression for the nth bright fringe. Fine. Now let's do this same for your dark fringes. Fine. Now again consider slit S1 and S2 and a screen which is placed at a distance d from the coherent source, and this point O is the center. Now let us consider this point A which is at a distance of x dash from the center O. Fine. Now consider the light coming from S1. 1, 2, 3 wavelength, 4 wavelength, 5 wavelength, 6 wavelength. So 6 complete wavelength. Okay. Note, I'm saying complete wavelength. Now let us consider from this point S2. 1 wavelength, 2 wavelength, 3 wavelength, 4 wavelength, 5 wavelength, 6 wavelength, 6 and half wavelength. Can you see? Half. So in this case, the extra path difference travel is how much? Half, lambda by 2. Fine. So in this case, the path difference is how much? Lambda by 2. Okay. So if you substitute this value here and you find out the value of n, how much is n? N will be 1. Fine. Now you substitute this value in the position x dash formula, this one. Fine. If you substitute this one, then your x dash can be written as half of d lambda by d. So at this point you will obtain the first dark fringe. That means there will be a black spot at here, dark fringe. Fine. Fine. Now let us consider another point B which is at a distance of x2 dash from the center. Now consider the light coming from S1. 1, 2, 3, 4, 5, 6, 7. 7 wavelength. Now light coming from S2. 1, 2, 3, 4, 5, 6, 7, 8, 9 and half. Okay, so the light coming from S2 is how much? 8.5 wavelength. Light coming from S1 is 7 wavelength. So if you subtract this value, how much you will get? 8 minus 7 is 1. 1 plus half is remaining. 1 plus half is how much? 3 by 2. So how much is the path difference in this case? It is 3 by 2 lambda. Fine. So let us write the value here. Fine. So for the path difference of 3 lambda by 2, the value of n is how much? 2. Substitute the 3 lambda by 2 and calculate this value. Okay, you will get n as 2. Now the position will be 3 by 2 d lambda upon small d. So at this position you will get a dark fringe. Fine. Fine. So in this case, if I keep on continue like this, you will get the dark fringe. But can you look at this pattern and tell me what is the what kind of pattern you are identifying? In this case, you will see that they are all the odd multiple. Fine. So to write down the odd multiple, what you'll do is first write down a even multiple. That is 2n. Okay, this is a even number. Now if I subtract 1 from this one, then it will be a odd multiple. That's why you see 1 here, then you see 3 here, then you see 5, 7. You can get those values using 2 and minus 1. Okay, substitute the values of 1, 2, and so on and check whether you get 1, 3, 5, and 7 or not. Fine. Now, after this, what else you notice? At the denominator, you have a 2. So you write down at the denominator 2. So I can write a general expression where your part difference equals to twice of n minus 1 lambda by 2. Fine. This is how I can write this expression, twice of n minus 1 lambda by 2. Now in this case, what will be the value of n? The value of n is n. Fine. And in this case, what will be the position? The position will be twice of n minus 1 upon 2 times d lambda by small d. So this is the position of the nth dark fringe. Fine. Fine. So we have found out the position of the nth dark fringe. So that's it for today's class. In our next class, we will derive the expression for the fringe width and we will solve some numericals on the fringe width. Okay. So that's it for today's class. Thank you. And if you have any confusion, please don't hesitate to ask. I will re-explain it to you again. So again, thank you.